Welcome back to Unit 3, Lesson 5. This is part 2 of the lesson. And we left off talking about how mutations can be described based on how they affect phenotype. But we can also describe mutations based on how they affect genotype. And by this, we mean how they affect DNA sequence. And we're just going to put down here as a reminder, recall, a change in DNA will cause a change in mRNA, which in turn may cause a change in the amino acid sequence of a protein. Okay, and just a quick question. Why did I say it may cause a change in the amino acid sequence? Think back to what we know about translation. That's right. We could not end up with a change depending on redundancy of the codons. If the nucleotide change still results in a codon that codes for the same amino acid because of redundancy, you would get what's called a silent mutation. You wouldn't even realize it's there because you'd still have the same amino acid. Okay. So the first main genotypic mutation we're going to discuss is what's known as a point mutation or a substitution. And while I want you to recall that these occur at the DNA level, I've shown how they would affect the mRNA because it's easier for us to look at how that will in turn affect the protein. So in this case, I want you to take a second and look for the mutation. Okay, you're playing spot the difference. Have you found it? Circle it, underline it, make it stand out somehow. That's right. In the third codon, it should start with G, but in the mutated sequence, it starts with U. Okay. Now when we go to translate, we can see how that might affect the protein sequence. So AUG, when we translate, we look it up on the codon table, is methionine. GAA, and I just have my codon table off to the side here. I haven't memorized these. Is glutamate, which is an E. GCU stands for an alanine, which is an A. And ACU stands for threonine, which is a T. I've chosen a word so it's a little easier to see the fact. Meat for protein. In the next one, we still have AUG for M, GAA for E, but UCU now codes for serine. We get mest. Different word, or in terms of translation of protein, an altered protein. Now, depending on how this affected the phenotype, it could then be a positive, negative, or neutral mutation. Okay. So at the end of the day, a point mutation is a mistake typically occurring during replication, where nucleotide is placed into what is supposed to be the complementary sequence. So there's a mispairing. And how big of an effect this has on the protein really depends on how different that amino acid is that replaced it. If they're really quite similar in their R groups, it might have little effect. If there's all of a sudden you have a positive R group in where you had a negative R group, you're going to totally change the three-dimensional structure of the protein and its function and possibly have a negative mutation. Okay. So that's the first and simplest mutation that can occur at the genotypic level. The next set of mutations are called frame shift mutations because they do what's called shift the reading frame. And they can include insertions where you insert extra nucleotides, or they can be deletions where you remove some nucleotides. Now these have a bigger impact because they don't just change a single amino acid, they actually change everything downstream for it. So if we look at the first one, in the first example being the insertion, in the second codon we've inserted a C. But because we read codons 3 nucleotides at a time, it shifts the whole frame. And a way to make an example of this is imagine you had a sentence like, the red cat ran. Okay, it's not a great sentence, but and then you accidentally inserted a letter N for then red cat ran. If you inserted the N, you would shift the entire reading frame, and everything downstream of where we put the insertion wouldn't make sense anymore. Okay. Well, the same is true when we're translating the mRNA. If there's an insert in the DNA, then you're going to have the corresponding insert in the mRNA, and it's going to shift the reading frame from what read M E A T. It's now going to read M. G C A is A. A G C is S. U A C is Y. And the U can't even be translated because it's a single nucleotide. This is a drastic change, and generally at a phenotypic level a negative mutation unless it wasn't an essential protein for function. Okay, so this here is just highlighting a shift in the reading frame. So the reading frame is normally where you would start, and whatever that start codon is, and then read it every 3 nucleotides down. We can look at this again as a deletion. this is deleted if you look at the bottom sequence, changing it from the M E A T to M A A G is lysine K, C U A is leucine L, and CU can't even be translated because it's not a full codon. Okay, so again, drastic changes. So insertions and deletions are kind of obvious. So you're either inserting an extra nucleotide or deleting your nucleotides, and especially devastating if how do I say this? If the insertion or deletion is not a multiple of 3 as it shifts the entire reading frame. Resulting in completely different codons downstream of the mutation. So instead of just changing one codon, you're changing everything downstream. As you can imagine, if it happens at the very start of the mRNA sequence at the 5' end, it's even going to be a bigger impact. If they're multiples of 3, you might just lose a single amino acid or gain a single amino acid, and it depends on the nature of that amino acid, how big of an impact that has. So if you're looking at mutation rates, they vary depending on species. They tend to be higher in bacteria, which reproduce more quickly and don't have as many proofreading mechanisms. In humans, it's approximately 1 base per 100 billion bases copied, which translates to about 6 mutations per cell division. Now, if you do the math, that 6 mutations seems a little bit low, but it's because we have proofreading enzymes that go back and correct some of the mutations. And as a result, there's about 175 hereditary mutations per generation, so from parent to child, you will have approximately 175 mutations or base changes compared to your parents. There are many factors that contribute to mutation. The first are simply errors made by DNA polymerase. During replication. And I'm just going to pause there because we're going to just run out of time, so I will stop it there as part 2 of the video, and you can pick up the last little bit in part 3.